In this class we discuss how the probability densities of the electron around the probability densities of finding the electron around the nucleus in a hydrogen atom, how these probability densities vary with the angular coordinates theta and phi. So let us call them angular probability densities. So we start this discussion with a theorem called Unsold Theorem. So this is Unsold Theorem. For any value of L, the probability density summed over all possible states from ml equals minus L to ml equals plus L yield a constant independent of theta or phi. Or if we write in terms of an equation, sum over ml from minus L to plus L. Okay, theta square. Theta depends on L and ml. Okay. So theta square into phi square. Phi depends on ml, right? This is equal to a constant. Okay. So this is the Unsold theorem, and further we can say that this means that any closed subshell of an atom. Closed subshell means all possible ml states are completely filled. So a closed subshell of an atom or ion has a spherically symmetric distribution of electric charge. Why do we say spherically symmetric? If we sum over all possible ml states for a given L state, if we sum over all possible ml states, that means all possible ml states are completely filled, let's say, then the summation over probability densities equal to a constant. It means that it is independent of theta and phi. Okay, that means it depends only on the radial variable r. So if we take from the nucleus, if we take a radial distance r, okay, to one direction, to another direction, to another direction, the probability densities vary only with the radial distance. It is independent of theta and phi. If all the ml states are completely filled, that's why we can say that for a closed subshell of an atom or ion, the electric charge distribution is spherically symmetric. Okay, and so let us try to verify this Unsold theorem first. Okay, before we want to study how the probability densities vary with angle, let us first see that this Unsold theorem is correct or not. That means if all the ml states are completely filled for a given L, then the sum of probability densities is independent of theta and phi. It's a constant. Now we can rewrite this Unsold theorem in this way. This angular azimuthal wave function, okay, which depends on ml and depends on the azimuthal angle phi. This azimuthal wave function, the normalized azimuthal wave function, is 1 by root 2 pi e raised to I ml phi, right? So what is the mod square of phi square? When you take mod square means phi star phi. When you take complex conjugate, when you take this and multiply with its complex conjugate, you get e raised to I ml phi into e raised to minus I ml phi, and the result is that exponential part will be 1. So what you get is 1 by phi square is 1 by 2 pi. Sorry, mod phi square is 1 by 2 pi. That means mod phi square is a constant. It is independent of, already it is independent of theta and phi. So that is why we say that the probability density has a cylindrical symmetry. It is symmetric about z axis. For all, it's independent of the angle phi, for azimuthal angle phi. If a quantity is independent of the azimuthal angle phi, it has the same value at a particular distance from the z axis. That means it has cylindrical symmetry, we can say. So since mod phi square is constant, we can remove that from this expression. Okay, so we can rewrite the expression for Unsold theorem as sum over ml from minus L to plus L mod theta square. Theta depends on L and ml. Mod theta square is equal to constant. Okay, Let us verify Unsold theorem for different states. So first let us consider n equal to 1, L equal to 0, that is 1 state. Okay. Now what is the value of theta for 1, 0 state? No. L equal to 1, yeah, when L equal to 0, what is the value of ML? ML is also 0. Okay, so it is theta 1, 0, and its value is 1 by root 2. Okay, so mod theta square is 1 by 2. It's a constant, so there is no need to do any summation because there is only one ML value for L equal to 0, which is ML is also 0. So here mod theta square is a constant. Now let us consider next state, n equal to 2, L equal to 1. Okay, that is 2s state. Now for 2s state, ML has values 0, also ML has values plus or minus 1. Okay, now for L equal to 1, ML equal to 0, the value of theta, that is 1, 0. Sorry, yeah, I think here I made a mistake. It is 0, 0. L equal to 0, ML equal to 0 in the earlier case. Now here theta 1, 0. Theta 1, 0 has the value root 6 by 2 cos theta. Now for ML plus or minus 1, okay, theta L equal to 1, ML plus or minus 1. Its value is the same for both plus 1 and minus 1. We get root 3 by 2, root 3 divided by 2 sine theta. Okay. Now let us do this calculation. Let us do this summation. Okay, sum over ML theta square. Okay. So what you get is sum over ML mod theta square is equal to, so let us take L equal to 0. When you take the square of that one, root 6 by 2 cos theta whole square, we get 6 by 4 cos square theta, plus then ML equal to, this is ML equal to 0, then ML equal to plus 1 and ML equal to minus 1. ML equal to plus 1 and minus 1, the expression is the same, root 3 divided by 2 sine theta. So we have 3 by 4 sine square theta for ML equal to plus 1, another 3 by 4 sine square theta for ML equal to minus 1. Okay, so we have 6 by 4 cos square theta, 3 by 4 sine square theta plus 3 by 4 sine square theta is 6 by 4 sine square theta. Okay, so the answer is we get 6 by 4 or 3 by 2. Okay, it's a constant. Sum over ML theta square is equal to 3 by 2 for 2s state. Now we can do this calculation for other states also. Okay, so for n equal to, you can do this calculation as a homework for n equal to 3, L equal to 2 state, that is 3D state maybe. Okay, so for L equal to 2 you have 5 different state, that is ML can be minus 2, minus 1, 0, plus 1 and plus 2. Okay, so consider the theta wave function. You can look at the table of hydrogen atom wave functions and you can take theta wave functions for different states, take the square and add them. So you can see, you can verify this Unsold theorem again, sum over ML mod theta square, theta L ML square. Okay, this is equal to, in this particular example this will be equal to 5 by 2. You can check that. Okay, so in all the cases you can, if you do this calculation, you can see that this summation is always a constant. Okay, if you add over for a given value of L, if you add over all possible ML states, okay, then the probability all possible ML states, if you add the probability densities over all possible ML states, this angular probability density is a constant. That means it is independent of theta and phi. It depends only on radial variable, so it's spherically symmetric, we can say. So this particular result, this unsolved theorem, it means that if we have no experimental measurement of the z component of orbital angular momentum, that means if we have no way of experimentally determining Lz, okay, it means that then the electron in the hydrogen atom can be in any possible ML state. Okay, if we know the value of Lz, it means that we know the value of ML state. But if we conduct no experiment to detect to measure the value of Lz, then the electron can be in any possible ML states for a given L state, for a given angular momentum state L. Let us say P state or D state or F state. It can have many different ML states. If we don't measure the Lz component of angular momentum, then electron can have any value of Lz. That means it can be in any possible ML states. Then we have now shown that if electron can be in any possible ML states, if we take the total probability density, angular probability, the probability density theta square summed over all ML states, then we get a constant. It's independent of theta and phi. Already we know mod phi square is a constant. Now we see that sum over ml or mod theta square is also a constant. So probability density is independent of angular variables. Okay, that means if we do not measure Lz, then we can say that the probability density of finding the electron is spherically symmetric. Okay, but in all situations of practical interest, there are some interactions. It can be chemical reactions, or it can be some applied electromagnetic field. So there are some interactions that determine this Lz component of the electron. Okay, so that means the electron occupies only certain specific ML states. Then the probability density will vary with ML. In other words, this mod theta square is it's no longer a constant. Okay, so probability density can have some angular dependence. So let us see how this mod theta square, okay, this angular probability density varies with this polar angle. Okay, it doesn't vary with azimuthal angle because mod phi square is the mod phi, the capital phi is the azimuthal wave function is the only wave function that depends on azimuthal angle, and mod phi square we have already seen it's a constant here. Okay, the azimuthal wave function is like 1 by root 2 pi e raised to iml phi. So mod phi square is 1 by 2 pi, it's a constant. So in the case of the probability density of electron in a hydrogen atom, it's independent of the angle, azimuthal angle phi. We say that it's cylindrically symmetric. It's symmetric about the z axis. So for all possible phi, the probability density is the same. What about theta? What about the polar angle theta? So if we have some interaction to measure the z component of the electron, maybe some applied electric field or some chemical reaction, so by which we measure the z component of the electron, then electron is in a particular Lz state. Electron has a particular Lz value, or it is in a particular ML state, we can say. Then this theta will be different, and this will vary with the polar angle. Okay. So this is the idea of angular probability densities. In Unsold theorem, say when the probability density is independent of the angle. When there are two possibilities. Either we do not measure the Lz component so that the electron can be in any of the ML state, or it's a closed subshell. That means all the ML states are completely filled. So in these two situations, the probability density is independent of angles theta and phi. It's already independent of the angle phi. In these two situations, it is independent of the angle theta also. That means it is spherically symmetric. But if the subshells are partially filled, and if we have some method by which we can measure the z component of the electron, now we know the ML state. Once we know the ML state, it means that we know that it's in a particular, the wave function, the angular wave function, the polar wave function theta has a particular value. Then let us see how theta varies with the polar angle. Okay. So let us consider the variation of mod capital theta square, the square of the polar wave function with the polar angle. Okay, so this consider the first feature of this variation. Look at the first topmost figure on the left side, left corner. Here L is equal to 0 and ML equal to 0. Okay, now when L equal to 0, ML equal to 0, the value of theta is, look at here, the value of theta, the polar wave function is 1 by root 2. So mod theta square is 1 by 2, which means that mod theta square is independent of the polar angle theta. Okay, it is the same in all directions. So that is why we can say that here when L equal to 0, ML equal to 0, this plot is spherically symmetric. It's actually a two-dimensional plot here. We will look at the three-dimensional plot after a while. So this is a two-dimensional plot. The vertical axis is z-axis and the horizontal axis represents the xy plane. Okay, so it's a circle. So if you rotate the circle around the z-axis, you get a sphere. So this is spherically symmetric, we can say, when L equal to 0 and ML equal to 0 for S state. For S state, the probability density is spherically symmetric. See, another point regarding this spherical symmetry of the S state is that here L is equal to 0. So what is the value of magnitude of orbital angular momentum? We know that the magnitude of orbital angular momentum is square root of L into L plus 1 h cross. So if L is equal to 0, the orbital quantum number is 0, orbital angular momentum is 0. But the probability density is spherically symmetric. But this is in contrast with a classical particle. What is the behavior of a classical particle? What will be the motion of a classical particle with zero orbital angular momentum? Okay, it will be oscillating along a line passing through the origin. Okay, the particle will be strictly oscillating along a line passing through the origin. Angular momentum is 0 because it is the line is passing through the origin. Okay. So this is the situation, this is the path, or this is the probability for a particle, classical particle with zero orbital angular momentum. But here in this quantum particle, electron in the hydrogen atom, even though for S state, okay, for each S state, the orbital angular momentum is 0, its probability density is different, it's spherically symmetric. Okay, so that's the difference between a classical particle with zero angular momentum and a quantum particle with zero angular momentum. The second feature is very important. Look at this, for L not equal to 0 states. Okay, as ML increases, right, look at here, for L not equal to 0 states, as ML increases, the probability density, that is mod theta square, changes progressively from mostly along the z-axis, from theta square changes from progressively from mostly along the z-axis to mostly in the xy plane. What does it mean? Let us look at the figure again. Consider, let us say, L equal to 1 case, okay, a P state. Now it has ML 0 value and ML plus or minus 1. See, look at the plot of mod theta square. For ML 0, the probability density is mostly along the z-axis. Okay, the lobes are mostly along the z-axis. But when you come to ML plus or minus 1, both plus 1 and minus 1, the figure is similar. See here, the lobes are along the xy plane, this horizontal. Here the lobes are vertical along the z-axis for ML equal to 0. Here the lobes are along the horizontal plane. So as ML increases, the lobes are, the probability densities are changing progressively from that along the z-axis to that along the xy plane. Look at L equal to 2 case. For ML 0, the probability density is mostly along the z-axis. And for ML, for L equal to 2, ML can be 0 plus or minus 1 plus or minus 2. So for ML plus or minus 1, it is intermediate between z-axis and the xy plane. Okay, let us say some 45-degree angle between z-axis and xy plane. So it's inclined at a 45-degree angle with the xy plane. Now when you come to the highest value of ML equal to plus or minus 2, the probability density is mostly along the xy plane. You can say that the orbit is flattened along the xy plane. Consider one more example, L equal to 3. For ML0, probability density is mostly along the z-axis, and for ML plus or minus 1 it's intermediate, plus or minus 2 again intermediate, plus or minus 3, the highest value of ML, probability density is mostly along the xy plane. So you can see that there is a progression. For each value of each non-zero value of L, as ML increases, the angular probability density for theta square varies from mostly along the z-axis to mostly along the xy plane. Okay, from vertical to horizontal. See here. See, if you come down, it moves from the probability density varies from vertical, that means mostly along the z-axis, to horizontal, mostly along the xy plane. Okay, and this trend increases with the L value. Okay, when the quantum number, orbital quantum number L increases, this becomes the orbits becomes more and more flattened. And as ML value increases, we have seen that as ML value increases, that means as we come down in this figure, ML value increases, and the probability densities are coming to xy plane, from along the z-axis to along the xy plane. So when probability densities are along the xy plane, we can say that the orbits are mostly along the xy plane. Okay, orbits are flattened. When the orbits are mostly along the xy plane, we know that the angular momentum direction, the direction of orbital angular momentum vector, is perpendicular to the plane of the orbit. So in these cases, when ML value is maximum for each L, ML is equal to plus or minus L. In this case, here ML equal plus or minus 2, ML equal plus or minus 3. So whenever ML equal to plus or minus L, the probability densities are mostly along the xy plane, means the orbit of the electron is flattened along the xy plane, and then the orbital angular momentum vector will be mostly along the z-axis, because angular momentum vector will be perpendicular to, is always perpendicular to the plane of the orbit. We can see that this illustrated here. This is the case of L is equal to 3. Then Lz can have values 0, plus or minus 1, plus or minus 2, and plus or minus 3. Okay, so here we have drawn only the positive cases. Okay, Lz equal to 0, plus 1, plus 2, and plus 3. So we can see that see, this corresponds to the last figure, last vertical column here. For L equal to 3, ML equal to 0, plus or minus 1, plus or minus 2, and plus or minus 3. That is plotted here. Else ML equal to 0 here, ML equal to plus 1 here, plus 2, plus 3. So as Lz increases or ML increases to the highest possible value, ML equal to plus or minus L, the angular the probability density is mostly along the xy plane. That means the orbits are mostly along the xy plane. Then the angular momentum vector will be mostly along the z-axis. Okay, and this trend increases with L value. Okay, to see that we can do a problem. Okay, consider this problem. What is the minimum angle the angular momentum vector may make with the z-axis in the case of L equal to 1 and L equal to 3? Two different angular momentum states. You can see that the angular momentum state is increasing. So we want to see what is the trend in this angle. So let us say this is the z-axis and this is the angular momentum vector. Okay. So if the angle between them is theta, if you drop a perpendicular here, this is Lz. Okay. Therefore, from this figure we can see that cos theta is equal to Lz divided by L. This is the magnitude of the angular momentum vector. Okay. So Lz divided by mod L. Say. Now, what is Lz? Lz is ml times h cross, and modulus of L, the magnitude of orbital angular momentum vector, is L into square root of L into L plus 1 h cross. So this h cross will cancel. Okay, we can say that cos theta is equal to ml divided by root of L into L plus 1. So in this expression, remember that from 0 to 90 degree, when theta varies from 0 to 90 degree, cos theta decreases. That means When theta is close to 0, if the angle is small, cos theta is maximum 1. When angle increases, cos theta decreases. So here we want to calculate in this problem what is the minimum angle the angular momentum vector may make with the z-axis. So this angle is minimum, very close to 0, when the numerator, this right cos theta, value of cos theta is close to 1. That means the numerator is close to denominator. The value of Lz is close to L. Okay, so theta is minimum when Lz is as large as possible. The z component is as large as possible. Or if we replace this Lz value with ml h cross and modulus of L with root L into L plus 1 h cross, we can say that theta is minimum when ml is as large as possible. Okay, so what is the largest value of ml? It is L, right? Plus or minus L. Let us take positive value. So ml, the largest value is L. So when ml is equal to L, okay, then theta, the numerator will be maximum, and then cos theta will be maximum closer to 1, theta will be minimum. That is the idea. Okay, so let us do this calculation for L equal to 1 and L equal to 3. Okay, so okay, we will do here for L equal to 1, ml has maximum value. Ml maximum is equal to 1 again, right? So what is cos theta here? Cos theta is equal to 1 divided by, denominator is put L equal to 1. So when you put L equal to 1, what you get is root 2. 1 by root 2. So which implies theta is equal to 45 degree. Okay. So this is the minimum theta. Theta minimum is 45 degree for L is equal to 1. What happens when L is equal to 3? The next is L is equal to 3. In fact, this figure illustrates L is equal to 3 case. So when L is equal to 3, then what is the maximum? We want to find out what is the minimum value of theta, then for which ml should be maximum. So what is the maximum value of ml? Ml maximum is again 3. So what is cos theta? Cos theta is equal to 3 divided by, when L is equal to 3, what is the denominator? Root of 3 into 3 plus 1, that is 3 into 4, that is 12. Now 3 by root 12 we can write as square root of 4 into 3. So root 3 and 3 will cancel, we get root 3 in the numerator, and square root of 4 will be 2. So cos theta is root 3 by 2. When cos theta is root 3 by 2, theta is 30 degree, and this is theta minimum. So we can see that as for L equal to 1 case, okay, theta minimum is 45 degree, and the angle between the angular momentum vector and the z-axis is 45 degree. The minimum angle is 45 degree. Whereas when L is equal to 3 case, okay, when L is equal to 3, so here when L is equal to 3, what is theta minimum? Theta minimum is 30 degree. Okay, that is you can see the illustration here. This is the L equal to 3 case, and theta minimum corresponds to the last figure on the right side, the bottom figure on the right side. Here the angle between the angular momentum vector and the z-axis, the minimum angle is 30 degree. So you can see that as the magnitude of orbital angular momentum vector increases, the angular momentum, the angular momentum vector, the direction of the angular momentum vector will come as ml value increases, it comes closer and closer to the more parallel to the z-axis. When ml value increases, the orbit will become more flattened along the xy plane. The probability density will be mostly along the xy plane. So if the orbit is mostly flattened along the xy plane for largest ml value, angular momentum vector will be more close to the z-axis, and this trend increases with L value. That is what we have seen now. For L equal to 1, it comes to up to 45 degree with the z-axis. For L equal to 3, it comes to 30 degree. So when you go to larger and larger L values, it comes more, and angular momentum vector comes more and more closer to the z-axis, parallel to the z-axis. That means the orbit, the plane of the orbit will be more and more flattened along the xy plane. Okay, so this is the second important feature of this variation of um, theta square with angle, polar angle. Okay, for L not equal to 0 states, as ML increases, the probable density changes progressively from mostly along the z-axis to mostly along the xy plane, as we can see in this figure. Okay, for each L not equal to 0 case, as we move down, probable density is initially for ML 0 case, it is mostly along the z-axis, but for the largest ML value, for ML equal to plus or minus L case, it's mostly along the xy plane. Let's consider two more features of this variation of probability density with the angle. This is the third one. In all ML not equal to 0 cases, probability density is 0 at the z-axis. Okay, if a positive particle is to have non-zero LZ, that means non-zero ML value, it must never be found on the z-axis. Okay, so if the value of LZ to be non-zero, that means ML to be non-zero, then probability density is 0 at the z-axis. Let us see this in the figure here. Consider the cases with ML not equal to 0. Okay, so here on the first row, first column, see ML plus or minus 1, probability density is 0 along the z-axis. Here ML plus or minus 1, plus or minus 2, plus or minus 1, plus or minus 2, plus or minus 3. So for all ML non-zero cases, okay, the right side corner, right bottom corner of this figure, for all ML non-zero cases, we can see that the probable density is 0 along the z-axis. So for LZ to be non-zero, its probable density should be 0 along the z-axis. And the fourth feature is this. In all L not equal to 0 states, okay, probable density is 0 at the origin. For all L not equal to, small l not equal to, so that means if there is some angular momentum, the probable density is 0 at the origin. A particle with angular momentum can never be found at the origin. Origin means the position of the nucleus. Again, you can see this feature in the figure. L not equal to 0 case. So L equal to 0 is only this one. For all L not equal to 0 case, the majority of the figures here, except the first figure, you can see that the probable density is 0 at the origin. So whenever a particle has some non-zero angular momentum, it will never be found at the site of at the position of the nucleus. So these are the four features of the variation of the angular probability density with the polar angle. Okay, mod theta square with the polar angle. Okay. Now we can combine this probable density mod theta square and the radial probable density, angular probable density and radial probable density. Then we will get mod psi square. That means mod psi square is mod r square into mod theta square into mod phi square. And if you consider the combined effect of all the three probable densities, we get the variation of probable density like this. With angle, it's like this. So we can see that the S state, L equal to 0 states, you can see is spherically symmetric, because for L equal to 0 state, the theta, already phi square is independent of the angle phi, but theta is 1 by root 2 for L equal to 0 state, so theta square is 1 by 2. So probable density mod psi square depends only on the radial variable r. It depends only on, it varies only with the radial angle, radial variable r. So it's spherically symmetric. So there are two figures here, 2s state and 3s state. Okay, yeah, 4s state is also there. You can see these three figures here. These are spherically symmetric. When you consider L equal to 1 state, or L not equal to 0 state, you can see that as ML value increases, the probable density moves from progressively changes from mostly along the z-axis to mostly along the xy plane. See, L equal to 1 case, 1s state to 1p state, that the variation is here. Then here also, yeah, 1s state to 1p state, 310, 311. So this is 3s state, 3p state from the z along the z-axis here, along the xy plane here. So this type of a trend you can see in all the figures. Okay, whatever we have deduced so far, that you can see in all the figures. The only difference here is that these are three-dimensional figures. The intensity of the shading indicates the probability density. If the intensity is low, probability density is low. If intensity is large, probability density is large. Okay, and these are three-dimensional figures which are obtained by rotating these two-dimensional figures around the z-axis. Okay, because cylindrical symmetry is already there. Once you draw the two-dimensional figures of mod theta square variation, we can rotate about the z-axis and we get the three-dimensional figures. And this is for theta square. If you multiply it with r square, then that is why at some points probability density is 0, where mod r square is 0. Okay, so that variation comes when you multiply with mod r square. So these are the plots of mod psi square, which is mod r square into mod theta square into mod phi square. Okay, so this is the main discussion or main details of how the probability density of electron in the hydrogen atom varies with angular variables theta and phi. There is no dependence on phi, but how it varies with theta, that we have seen here.